Welcome all of you to the today's class, Chemistry of Soil Potassium and its Transformation. How the potassium is taking transformation like other nutrients such as nitrogen and phosphorus we have seen in the earlier slides, earlier classes. So we will see how the potassium is getting transformed in the soil. Before entering into the content, you need to know what are all the functions of potassium in plants. Potassium is very important element which is involving in carbohydrate transport and storage, and it is uh, involving in energy related reactions and water related reactions, because this potassium is uptaking by the plants in the form of ionic element, which will not combine with any other oxygen or hydrogen molecule, since it is a K plus ion which is uptaken by the plants in this form itself. So it is like a freelancer, it can move everywhere to the plant. So it is very important. That's why it is called traffic policeman. This element is called traffic policeman. There won't be any stoppage in between the plant pots. Simply from once it is uptaken by the plant, it will taken to the entire part of the plant, and it is also supporting for nitrogen uptake and protein synthesis, cell development, strong walls. So these are all the important functions of potassium in plants. Why potassium? Nitrogen is indicating with the symbol N, phosphorus is indicating with the symbol P. They are first lectures. Why potassium is indicating with K? The answer is, in Latin word, potassium is called kalium. Kalium. Kalium means potassium. In German, Kali. The first letter is K. In Latin word, first letter is K. That's why potassium is referred as K. In the soil, earth crust, the potassium contains nearly 1 to 4 percentage. The plant contains 2 to 10 percentage. It is more than nitrogen and phosphorus present in the plant. Nitrogen is a heavy absorbed nutrient by the plants, but at the same time, potassium is much more heavy absorbed nutrient by the plants. The form absorbed by the soil is K plus. That's what I have been told you, that it will not combine with any other molecules. It will not form any compound. Okay, hydrogen, oxygen, nothing. So it is available to the plants in ionic form, K plus. So it can be transported to the plants through mass flow and a diffusion process. Sandy and low organic matter soil are frequently potassium deficit. Potassium deficit. You can see the potassium bearing minerals. Potassium feldspar is the dominant one, followed by muscovite, biotite, and secondary clay minerals, the organic matter. These are all the main sources of potassium in the soil. Potassium feldspar, if you see, potassium aluminosilicate compound. This is also potassium aluminosilicate, and biotite contains potassium along with magnesium ion in their compound, as well as the aluminosilicate. And clay minerals, mica. This is called mica. Then biotite, muscovite, illite are the secondary clay mineral, which are all bearing the potassium to the soil. Then organic matter, organic matter addition to the soil will improve the availability of nutrient from the soil. You can see the potassium cycle here, like there are different components you could see. The green color indicated components are the forms of potassium in soil. So obviously, soil solution potassium, solution form of potassium is a dissolved nutrient concentration and which will be directly available to the plant. Okay, soil solution. The new element must be dissolved in soil water to convert soil solution, then only it can uptake by the plant. And we have seen some of the mineral feldspar, aluminosilicates. So these are all the mineral potassium. Mineral potassium, when they are weathering in the soil, that will release the nutrient to the soil. So when it is weathering, it will become a soil solution potassium. Some soil solution potassium will be fixed by this mineral once again when unfavorable condition is established in the soil. And exchangeable potassium. Exchangeable potassium is absorbed by the soil particle on their surfaces. K plus. K plus is absorbed because of the electrostatic potential of the clay mineral. Clay having negative charge. So negative and positive has greater affinity so that they are absorbing on the surfaces. They are exchangeable. Why it is called exchangeable? It can equilibrium with the soil solution. Faster, rapid equilibrium. Of course, all the three are having equilibrium, but the soil solution K and the adsorbed K having a greater equilibrium or very rapid equilibrium rather than this mineral potassium to exchangeable or mineral potassium to soil solution. The inputs, if you are see mineral fertilizer like a muriate of potassium sulfate, different fertilizer we are applying, straight away it will comes to the soil solution form because the nutrient will dissolve in water and it will comes to soil solution. Likewise, decomposition of plant and animal residues or some organic manures which also will provide the nutrient in the form of soil solution. Losses, if you see, leaching losses will take place as well as runoff will take place when the unfavorable condition is approaching to the soil. Here you can see this is soil solution readily available form, and we have seen in the previous one exchangeable and mineral. They are having equilibrium with soil solution. You can see they have not indicated the reverse equilibrium of soil solution to mineral. Just it is weathering, and they have indicated with that slow processing. When it is weathered, it will bring the nutrient to soil solution. At the same time, you can see the exchangeable. The exchangeable, they are here. You can see they are attaching on the surfaces of the clay minerals so that it can easily comes to the soil solution. Also, they have mentioned it is a rapid form of equilibrium. At the same time, absorption also taking place in a very rapid form. So the opposite uh, term of adsorption is desorption. Once the element is desorbed, it can comes to the soil solution from the surfaces. Okay. So next coming to fixed potassium. Fixed potassium nothing but the potassium are uh, fixed in between the layers. Fixed in between the layers. This is clay mineral, the upper surface and lower surface clay mineral. In between this interlayer space, the potassium will fix very tightly so that the fixed potassium is developed here. So it is also having equilibrium with the soil solution. You can see. So if you see the process, how the process is taking place, whether it is slow process or rapid process, the mineral once it is weathered, it may be fixed by the clay mineral or it may be comes to the soil solution depending on the condition. Okay, so both the process are taking in a slow manner, and the fixed K, when this potassium coming in the soil surface, the potassium is ready to come to the soil solution. This process also a slow process. Okay, but the absorption and desorption, they are straight away connected to the soil solution, so their process is very, very fast. You can see some characteristics of potassium here. Soluble potassium in soil is not very mobile in soil because I have been telling that clay minerals having negative charges on the surfaces, so they can easily grab the potassium ion or any other positive ion. That's why the movement of potassium in the soil is not very mobile. But at the same time, in plant, their movement is very, very fast because they are uptaking in a ionic form. Yes, you can see potassium is extremely mobile within the plant. And potassium is not supplied from decomposing soil humus because it is not part of the combination of humus. Other nutrients can be released, potassium is not released. But this organic humus or any organic matter, when you are adding into the soil, that may facilitate for the existing availability of potassium from the soil. And it is a positive ion, moves slowly through soil. That's why I have told a reason to you. The immediate crop obtains all potassium from soluble and exchangeable form. So soluble form means soil solution, and exchangeable form. Exchangeable form is the form which is ready to equilibrate with the soluble form. So they are known as immediate crop obtains. Sometimes the exchangeable also supply the nutrients. Sometimes, not all the times. Okay, to the plants, directly connected to the plants. There is some competition for uptake among the nutrients. Yes, absolutely, because the potassium is a positive ion. Similarly, calcium is a positive ion, magnesium is a positive ion. Among these ions, the competition will be taking place. Which ion can be placed in the mineral surface? Which ion can be taken by the crops? This kind of competition will be taking place. So it is very important, the forms and availability of potassium, how much potassium is available. You can see here the soil solution and exchangeable potassium regarded as the available form of potassium, and the difficulty exchangeable is unavailable to the plants directly, and mineral potassium also in the similar way. So soil solution potassium is very, very lowest concentration, just 1 to 10 ppm, and exchangeable potassium 40 to 600 ppm. So from here, the equilibrium will happen once the soil solution potassium is being uptaken by the plants. And here difficulty exchangeable. They are fixed potassium. This potassium is called fixed potassium. This fixed potassium having very higher amount concentration, like 50 to 750 ppm. And mineral potassium, it is a reserve of potassium having 5,000 to 25,000 ppm. And percentage wise, if you see, 98 percentage of 90 to 98 percentage of mineral potassium are available in the soil, and slowly available is 1 to 10 percentage, and 0.1 to 2 percentage, which is very lowest concentration, that is 1 in ppm. We can say it 1 to 10 ppm soil solution potassium. The transformation of potassium in soil. Here you can see potassium ion. If you see 6 to 45 kg, in kg they have mentioned, they are available in soil solution. This is the fast equilibrium, exchangeable potassium to potassium solution, and this is a slow process, very slow process between exchangeable potassium to slowly exchangeable potassium or fixed potassium, that is layers of clay minerals, and potassium in lattice, that is soil silicates or mineral potassium. Okay, so in kgs they have given in different numbers, 6 to 45, 3000, sorry, 300 to 1600, and 3000 to 11,000, and above 11,000 is potassium lattice. This picture clearly explaining how the structural potassium and fixed potassium and the adsorbed potassium are there. The soil solution where the potassium can freely move. You can see there won't be any surfaces for the attachment. They are so freely moving in the soil solution, but at the same time, structural potassium. For example, illite. Illite is a potassium-rich clay mineral. You can see this potassium are just attached to the uh, means naturally present in the surfaces. But at the same time, fixed potassium, they are not present in the surfaces of the clay mineral, but instead they completely trapped between these two layers. Okay, this potassium means adsorbed potassium, neither structural nor in between the layers, just attaching on the surface. Anytime it can comes to the soil solution. Okay, this is what the difference between these three. As we have seen, the solution potassium and exchangeable potassium having the rapid equilibrium, whereas the exchangeable potassium and the non-exchangeable potassium is having very slow equilibrium. The soil solution potassium, one by one, will see all the forms of potassium. The soil solution potassium dissolved in soil solution and exist as potassium plus form. And it is a plant available potassium equilibrium with exchangeable potassium that we have seen in the previous slide too. Exchangeable potassium, they are considered as plant available, but not all the times. Like calcium, magnesium, sodium, aluminum, hydrogen, they are also a positive ions. These positive ions held on clay. Similarly, the potassium also held on clay. So 150 milligram per kg, that is 150 ppm, is considered high enough to ensure potassium sufficient in plant. If the plant having 150 ppm, that is enough. Such potassium equilibrate with 1 hour with solution potassium in most soil. Less than 1% of the total potassium occur in this form, like exchangeable form. Less than 1%, very lowest amount. The next one is non-exchangeable potassium. It is not removed by exchanger but plant available. Very limited amount of potassium is being taken up through this form. Most of the potassium is available through the solution potassium, but the non-exchangeable potassium also little bit supports for the plant. The potassium is fixed by vermiculite, montmorillonite, and other 2:1 type of clay mineral is referred as non-exchangeable because the potassium which is present in the minerals or which is locked up by the minerals like vermiculite, montmorillonite are 2:1 type of clay minerals. Okay, they are non-exchangeable and in equilibrium with exchangeable K. So the solution is rapid equilibrium with exchangeable. This exchangeable is slow equilibrium with non-exchangeable. Okay, this is the order of the equilibrium is taking place here. Then mineral potassium or reserved potassium. You can see the crystal structure. Part of crystal structure of clay mineral occupies interlayers of micaceous mineral, including 2:1. In between the layers, the potassium is being fixed or locked up. Okay, they are reserve potassium or mineral potassium, not plant available because it has to come out through any replacement that is called isomorphous substitution. Like any other ion, positive ion will come and replace this potassium, then potassium will comes to the exchangeable form, then plant solution form. The solution form is straight away supplying the nutrient to plant. Okay, this is the order. And there are some primary and secondary minerals are having potassium. Like primary minerals we have seen in the beginning, like feldspar, orthoclase, and microcline. Feldspar containing orthoclase and microcline having 13.7 and 13.8 percentage respectively. And mica, biotite is known as black mica and muscovite is a white mica having 8.7 and 9.8 percentage respectively. Similarly, the secondary clay mineral like 1:1, 2:1 type of clay mineral. The illite is a 2:1 non-expanding type of clay mineral, which is almost contributing 7% of potassium of the primary source. Here you can see how the transformation is taking place from the mica to secondary clay minerals. So mica is a primary clay mineral. Particle size is very, very large. Okay, like a stone. This mica will absorb the water and become hydrous mica. So once the water is absorbed, it will become a swelled mineral. The swelled mineral slowly release the release the potassium. So once it is absorbed the water, it will become illite. Then the illite will produce montmorillonite as well as vermiculite. Here you can see initially the potassium percentage is 10 and it becomes 6 to 8 percentage and 4 to 6 percentage, slowly 3 percentage, then finally less than 1 percentage of potassium only available. And if you can see the CEC, and this is 0 milli equivalent, there is no, because of the particle size is very higher, it has to undergo weathering process. So once the weathering process is taking place, the particle size or surface area will increase. Okay, when the surface area is increasing, the number of finest particle also increasing. So the C is also increasing towards the finest particle or increased surface area. Like C is here 0. When it is come to illite to hydrous mica, uh, uh, mm, between it shows 30 to 50 milli equivalent. And here the montmorillonite vermiculite are always having higher CEC because like nutrient exchange capacity, cation exchange capacity, 140 to 160 milli equivalent per liter. This already we have seen the equilibrium, how the equilibrium is taking place, slow equilibrium, very slow equilibrium, and rapid equilibrium between the different components. Welcome all of you. In this chapter, we are going to see the factors affecting availability of potassium in soil. There are a lot of factors affecting internal factors, external factors. Among that, internal factors are very important. That what all the factors are affecting the availability of potassium in the soil, we will see. What are the factors affecting availability of potassium in soil? There are different factors, a lot of internal factors like soil pH. Under acidic condition, available potassium is reduced due to effect of iron and aluminum ion on root. Because the iron and aluminum are dominant in acid soil, since they are positive ions, it will compete with this potassium ion. So the lowest pH soil or acid soil is always unfavorable for potassium. Next, parent material, the feldspar. Wherever the feldspar is present, the availability of potassium is also very higher. Cation exchange capacity. If there is more CEC, high potassium availability or high potassium exchangeability, and texture, fine texture soil like a clay soil held more exchangeable potassium, whereas sandy soil has very lowest amount of potassium. Amount of exchangeable K, if initial exchangeable K is high, then higher potassium uptake is noticed in graphs. Soil moisture, high soil moisture, greater diffusion means dissolving of potassium, and higher availability of potassium is also taking place. Soil aeration, aeration should be optimum or good. Otherwise, the poor aeration will lead to the unavailability of potassium or lower absorption of potassium. Soil temperature, soil temperature also should optimum. Lower soil temperature always lower the availability. Presence of calcium, magnesium. Already we discussed about it. The calcium and magnesium is a positive charged ion which will compete with the potassium present in the soil. Then capacity to fix potassium. The soil rich in micaceous mineral will have more potassium fixation capacity, so that the mica rich mineral always supply higher amount of potassium to the factors influencing exchangeable K. What are the factors are influencing? Different factors are there here. One is wetting and drying, means presence and absence of water, which leads to the increase, which govern the increase and decreasing of nutrient, and potassium fixation also governed by this wetting and drying, and potassium release can occur by the wetting and drying. So how the exchangeable potassium is increasing or decreasing when soil is dry? Once the soil is dry, the potassium availability also get reduced. It is also depending upon the clay minerals present. What kind of clay mineral? 2:1 type of clay mineral or 1:1 type one type of clay mineral. And fixation. If the soil has high exchangeable potassium, uh, and recent potassium fertilizer is added, or dried. And fixation is a result of potassium becoming trapped within clay sheets. I have told you that this is the layer silicate sheets. Between these layer silicates, they will be entrapped. Okay. And when it become very dry and uh, brittle like nature, the potassium fixation will occur. When the potassium release will occur, then soil low in exchangeable potassium or dried condition, the clay sheets roll back and release potassium. They will roll back and release the potassium. During the time potassium release can occur. You can see clearly the potassium fixation. So this is illite. Illite is a potassium rich mineral and a non-expanding type. This layer silicate, the layer silicates will not expand from their structure. Expansion means the increasing the size in the upper and the lower side because of the pressure creating inside. So here you can see the potassium is present everywhere, interlayer space and surfaces everywhere because potassium rich mineral. But at the same time, you can see vermiculite. Vermiculite is a expanding type of clay mineral. Expanding type of clay mineral. They will expand their structure. They are having potassium in their interlayer. During the dry period it will lock very tightly, but at the same time when it is get absorbed by in the water or swelling in nature, the potassium may be released outside, okay, in vermiculite. Here, the same example, illite is non-expanding, so that they are very closely attached. Okay, showing very close, like this is interlayer space, this is outer space. So where the minerals are locked up. But in the Montmorillonite, this is expanding type of clay mineral. When the layers are getting expanded, the minerals are looking very free, so it can comes out anytime. But in the kyanite, it is a non-expanding type of clay mineral where you cannot find any kind of minerals locked in between the layers. They always present in the surfaces of the clay sheets. Okay. How the potassium is releasing from the exchangeable and the non-exchangeable. Okay, so this is exchangeable potassium, this is non-exchangeable potassium. The exchangeable potassium, they are having the potassium on the surfaces, means absorption on the surfaces. Okay, so once the equilibrium is happening between the soil solution and exchangeable potassium, the potassium is go to the soil solution immediately because the rapid equilibrium is taking place. Equilibrium nothing but the presence of the potassium in equal amount both in the soil solution as well as the exchangeable sites of potassium. Once the potassium is getting absorbed by the plant, here the potassium depletion will take place. To compensate this potassium depletion, the exchangeable potassium will come and replace the losses. Okay, this is what the equilibrium. This process happening in very fast manner. But at the same time, this is non-exchangeable potassium where the potassium not easily comes to the soil solution. One ion has to be replaced the potassium ion like calcium. Once the calcium is entered inside, it will find a place here, and the potassium has to comes out. So thereby the potassium is coming into the soil solution. Okay, this is non-exchangeable potassium. Slowly it will come and become a exchangeable one, right? So Page and Weber in 1940 they have uh, they have told a lattice fold theory. The potassium size, ionic size of potassium is very close to the lattice hole. Lattice hole, nothing but a layer will be there. In that layer, there will be a hole where the potassium will be locked up. Okay. The potassium ionic size as well as the hole present in the layer silicate size also very similar, so that the potassium can come and easily sit on the hole. That theory was given by Paver and Badge. This theory is known as lattice hole theory. This is lattice. In this lattice, there is a hole. So where potassium is trapped. This theory is called lattice hole theory. So the intensity of potassium fixation is zero with kaolinite because it is not expanding type. Fixation will not happen. In the previous slide also we have seen in between there is no ions. Okay, no potassium, only they are present on the surfaces. Okay, chlorite also in the same way. The chlorite 2:1:1 type of clay mineral where it is a non-expandative and slight with montmorillonite, variable with illite, and strong with vermiculite. Okay, vermiculite is a partially expanding type. This vermiculite also we have discussed in earlier, and the montmorillonite is a highly expanding, so that slight fixation will take place. Okay, but variable with illite and strong with vermiculite. Okay, so this is happening because of cation exchange capacity. Cation exchange capacity also varies with the clay minerals, so that the potassium fixation also will get vary here. What are all the factors affecting potassium fixation? One is type of clay mineral. What type? We have seen that kaolinite non-expanding and vermiculite is partially expanding and montmorillonite is highly expanding. So depending on the type of clay mineral, the potassium fixation is taking place. Similarly, alternate wetting and drying, freezing and thawing. This also we have discussed in previous slide. When the potassium is releasing, when the fixation is happening during the wetting and the drying time. And the soil pH. Here also we have seen the iron and aluminum will compete with potassium, or else the iron and aluminum keep potassium ion from close association with colloidal surfaces, means in the clay surfaces. Okay, so uh, which will make the potassium is not absorbed by the colloids, but they are always absorbed ions of iron and aluminum, which will keep the potassium very closer to this. It will prevent the absorption. Okay, but when you are applying the lime nothing but a calcium carbonate, which will be applied to the acid soil. Once the lime is applied, the iron and aluminum activity will be reduced. Okay, so potassium move closer to the colloidal system and it will get fixed. Okay, this is what happening in soil pH. Okay, so the iron and aluminum is hinders the fixation between the colloids and potassium. Once the aluminum and ion are removed from the soil by applying lime, the potassium is fixed on the colloidal surfaces. What are the losses of potassium? There are four losses. Crop removal. This is must be happen, and leaching, erosion, and soil fixation. These are all the four important loss. The erosion is very minimal here because the potassium is less mobile nutrient in the soil. Sometimes if there is any flood and all happen in the soil, the erosion may take place. Leaching also very small here. Okay, but the soil fixation also another problem depending on the soil pH condition. The leaching losses of potassium. They are largely observed in sandy soil because sandy soil has less nutrient holding capacity, so leaching is happen. But in the clay soil, the leaching is very, very minimal. In humid tropics, leaching the major factor limiting in productivity means in the high rainfall zone where the leaching is a biggest problem, which will limiting the productivity because of the losses of potassium. The potassium source also influence the leaching loss. Okay, uh, what kind of sulfate based or chloride based or different potassium sources also. Compared with the potassium chloride, that is muriate of potash, the sulfate and phosphate sources exhibit greater anion absorption. Hence, leaching loss is low. Okay, sulfate and phosphate sources, potassium sulfate and potassium phosphate. Okay, they are anion absorption. Their absorption is very high, so that the losses are very, very less. Crop removal. Crop removal is very high potassium or high amount of potassium will be removed here, like 3 to 4 times of that phosphorus and equaling that of nitrogen. Almost equal amount of nitrogen and 3 to 4 times of phosphorus is absorbed by the crops. Okay, in terms of potassium. Sometimes the losses of potassium is made more critical when plant take up for excess of its requirement. Sometimes what will happen, the potassium is being uptaken continuously by the plant. Okay, more than the required amount. So this process is called luxury consumption. This luxuriously, the potassium is continuously taking up by the crops. Okay, so this luxury consumption is only associated with the potassium. Okay, luxury consumption. Coming to intensity and quantity ratio means the power of soil to supply potassium to plant roots is described in terms of intensity and quantity. What is the power of soil there? How the potassium supply is maintained by intensity and quantity factor. If you see, the intensity factor is a measure of the potassium that is immediately available to the root, immediately available to the root. Okay, and the quantity factor is capacity of soil to manage the level of potassium in soil. How much level of potassium is maintained in the soil, how much potassium is immediately available to the crops. Okay, how much potassium is maintained is called quantity. Quantity of potassium is maintained, and the potassium is how much potassium is readily available to the plants. So this ratio between these factors is called quantity and intensity. This is quantity, how much potassium is managed, then intensity, how much potassium is readily available to the plants. So this potassium also is uh, relate with the calcium and magnesium, since we have seen the reason earlier. They are positive charge, so that this also will affect the potassium ratio here. And buffering capacity, it is also very important. It is also depending on the quantity and the intensity ratio. Buffering capacity of potassium, K plus ion. So this concept of buffering capacity of soil indicate how the potassium level in the soil solution is varies with the amount of labile form in the element. So buffering, how the potassium is varying or maintaining in the soil is depending upon the intensity and the quantity. Okay, in soil solution and amount of labile forms in this element. Okay, labile form means it is readily available form. Okay, so this ratio will change when the quantity factor is changing and intensity quantity factor to the changes in intensity factor. Okay, their ratio also change. So this, if the ratio is very high, the soil has good buffering capacity. At the same time, if has low ratio between qi, they are having very lowest buffering capacity. Okay, clay textured soil having more buffer capacity than sandy soil. Clay always having because absorption is very, very high here. Okay. Thank you so much.